Hey, welcome back. Today we're going to be talking through how to solve electric field problems when you're dealing with a point charge and the derivation of the equation from Coulomb's law. So I'm going to show you how you come up with a second version of the electric field equation. I'm going to show you both of the main equations used for a physics or maybe even a physical science class and where you get one of them from another, and show you how to solve a problem related to what we're talking about. So remember, this is our phenomenon that we're dealing with. You probably have done this before, where you get a balloon and you rub it against your hair, and then after a while your hair and the balloon attract each other because electrons are being rubbed off the hair onto the balloon. And so we want to think about what electric fields are and how those involve an electric force, and that's the point of this lesson here. So let me show you the math involved of how to do something like this. Alright, and so one thing we're going to do is treat the balloon as if it is a point charge. So we're going to call that a capital Q. You could call it a lowercase q as well. And let's make it negative. We're going to make this negative because the balloon is picking up negative charges. And so that would mean that you have electric field lines going into this. And I've done a screencast completely on electric field lines. I'll put a link to that in the upper right about now if you need a little bit more help on this. But the electric field lines are going to be pointing into a negatively Q charged object because a small positive test charge would be attracted to that negatively charged larger object. And next, one of the key equations that we may or may not have talked about up until this point is the definition of an electric field in a mathematical sense. We're going to say an electric field is equal to the force that is experienced by a small test charge divided by that test charge. So that's what we're talking about when we talk about an electric field. This is a very important equation. I can label this as equation 1 right here. But what we can do also with equation 1 is remind ourselves we know something about that F electric. We can say we have talked about Coulomb's law, and I could put a link to that lesson in the upper right about now if you want more information about that, but it's just describing the force that you get between two charges. So we can go ahead and sub that in if we know something about Coulomb's law. So let's see what happens if we do that. So we can say our electric field is equal to Kc times, let's think about what Q1 and Q2 would be in this equation here. I'm going to change this from Q1 and Q2. Let's call this capital Q, and let's call this Q2 down here. So capital Q is going to represent the charge that the balloon has. And then the other Q that we have down here would be a small positive test charge. We can label as Q2. And so again, all I'm doing is changing these subscripts right here. So this is a subscript, for instance. A subscript is just a label there for us. These can be changed to more clearly modify what we're talking about. And a capital Q can be substituted in for a lowercase q as well. They're synonymous in the context of what we're talking about here. But just to be clear what we're talking about, I'm going to say, all right, let's call this a Q2 over here divided by this Q2 that was already there times our R squared. And let's think about what happens here with this. So notice we've got a Q2 here and a Q2 here, and we can cancel those out because they'll reduce to 1. So what are we left with? We're left with, in this equation, the electric field is equal to Kc times the big charge that's producing the electric fields in the area that we're considering, divided by the R value, the distance in between the center of both charges. Now notice this electric field it's independent of the test charge. What that means is this electric field tells us something that it doesn't matter if you have a large charge for Q2 here, this original Q2 here, or a small charge for Q2 here. It simply doesn't matter because we're going to divide out that Q2 anyway. And that's one of the reasons why fields are so useful. They're telling us something that's independent of whatever it is we're testing it by. We still learn something that's important about that point in space. In other words, this point in space right here with reference to the big charge. Well, if that's the case, then we can go ahead and solve a problem like this. And that's what our example problem is. we can call this 8.99 times 10 to the 9th. Some teachers will summarize that as 9 times 10 to the 9th. And that's our setup for the equation. And if we do the calculation, your answer turns out to be this. And we're going to end up with an answer in newtons per coulomb. And what that tells us is the more charge you put in there, the more newtons of force would be applied on that object. And that's really what we mean by an electric field. I do want to emphasize that this right here is the second really big equation that we can use for determining electric fields. So let me bring this back up here. We had this first equation, which is a definition of an electric field over here. And for number 2, we're talking about this is the electric field as determined from a point charge. So now we've got 2 equations to work with for solving electric field problems. Hopefully this has been helpful. If you have any questions or comments down below, please let me know. And I hope you all have a great day. Take care.